Hello, Professor. I hope you are doing well. Today, I'm excited to share our presentation on detecting loan application fraud, a machine learning framework for loss prevention and operational efficiency. In our group, we have 5 members. First is me, Parimala. Second, Sudis. Third is Wong. Fourth is TEOH. And the fifth is KAMINI Devi. In chapter 1, this is our executive summary. Online loans are fast and easy, but that also makes it easier for fraudsters to cheat the system. This project uses smart technology, machine learning, to spot fake loan application and stop them before the money is paid out. Here, the GX booth is our best model, detecting 57.3% of frauds and saving the bank USD 1.3 million per batch, projected to reach USD 44.3 million annually. Our chapter 2 is problem statement, or we call as problem definition. Online loans are very easy to get and very fast. But scammers use fake identities, fake documents, fake income, and they do group attacks like the syndicate attacks to cheat the system. Missing a fraud case can cost about USD 8K, while rejecting a real customer wrongly only costs 45 USD. So, using a smart system to stop fraud early helps bank save the money and treat honest customers fairly. This makes the leading system safer and more trustworthy.
Moving into Chapter 3, let's look at our core data strategy. We are deploying a supervised cost-sensitive machine learning frameworks. This target for distinct loan types across 6 major Indian financial institutions. The data quality shows perfect health. We are working with exactly 1,000 rows and 12 columns with 0 missing value and 0 duplicates records. The strongest correlates for fraud are clearly behaviors, anomalies, high device change rate, max out, applicant, occasion, frequency, and unusually short season. Its high exposure mix, about 50% of applicants have IP region mismatch. Nearly 29.5% have prior defaults, and the loans amounts scale all the way up to 1.28 million. Next up is the target variable distribution. Legitimate applications make up 83.92% of the data, while fraudulent is 16.08%. A naive model could just predict legitimate triggers with a fake 88% accuracy scores. We apply XGBoost set to 5.22 to heavily penalize misclassifying those fraud cases. Let's talk about feature engineering. We started by one hot encoding institution, expanding our dataset from 12 to 18 columns. We built 3 interaction features to catch complex fraud patterns that brought our final dataset up to 20 variables.
In Chapter 4, I'm going to show you how we actually build our model. So basically, we have 10,000 loan application and we split the data into 70% for trend and 30% to test it. And we make sure the fruit rate stayed at the same for both around 18%, so the test is fair. After that, we build 2 models. The first one is logistic regression, thinking of it as a very simple and easy to explain model. Many bank and regulation like it because they can see how exactly it works. The second one is XGBoost, more powerful, better at picking out the complicated fruit pattern. The key thing here is we didn't ask which model is more accurate, we also asked which model saved the bank more money. So that is what drives everything in this chapter. First, we test both models at the standard setting, threshold 0.5. At this setting, logistic regressions only catch 22% of fraud. XGBoost did a bit better at 24.5%. The same threshold, same data, but it catch more than 10 frauds. That is 80,000 saved. The downside is 35 more false alarm, but it only costs 1,000 plus to review. So the bank is 78,000 better off by switching to the XGBoost. The normal threshold 0.5 treat every mistake the same. but they are not in this case. Missing a voice that means the bank will lose 8,000, but flag a good customer wrongly, it costs only 45. The ratio is 178 to 1. So we test every threshold from 0.3 to 0.7. Look at the chart. The bottom of the curve is at 0.3. So at 0.3, the fraud recall jumped from 22 to 57%. The total cost dropped 44%. That means at 100,000 loan a year, there are a 44 million saved. So the big takeaway is not only building a model, but it also making a smarter decision on where to set the line. And this is the model we suggest.
Hi everybody, I'm KAMINI Devi RAVEENDRAN with matrix number 25102172. Today I'll be explaining on chapter 5, which is results and model comparison. This chapter compares different fraud detection models based on predictive performance and economic impact. The results show that XG Boost with threshold optimization at 0.30 significantly outperformed the logistic regression baseline. Fraud recall improved from 22.4% to 57.3%, showing a major increase in fraud detection capability. More importantly, the total economic cost was reduced from US dollars 2.996 million to US dollars 1.666 million, resulting in a 44.4% reduction and approximately US dollars 1.33 million in saving. The findings demonstrate that threshold calibration is a key value driver because aligning the model with actual fraud causes can greatly reduce financial exposure. Although the optimized model slightly increases manual reviews, the operational cost remains small compared to the fraud losses prevented. Therefore, XG Boost at threshold 0.30 was selected as the best model due to its higher fraud detection, lower economic loss, and stronger business value. In conclusion, this study proves that effective fraud detection is not just about using a complex model, but about optimizing the model based on real economic impact. Moving on, this slide highlights the financial impact of the optimized XG Boost fraud detection model. The key finding is that the missed fraud cases contributed 98.9% of the total economic cost, while false positive investigation costs remain very low at only 1.1%. Using XG Boost at threshold 0.30 reduced the total economic cost to USD 1.666 million, showing that better fraud detection creates direct financial benefits. When projected to 100,000 annual loan applications, the model could potentially reduce total cost from USD 99.9 million to US dollars 55.6 million, generating an estimated annual saving of US dollars 44.3 million. Overall, the findings confirm that the optimized XG Boost model provides stronger fraud protection, lower financial loss, and greater long-term business value for financial institutions.
Moving on to chapter 6, model interpretability, which is a critical component of any AI system used in financial services. Interpretability is not optional. In regulated environments such as banking and lending, institutions must be able to explain and justify automated decisions. Regulatory framework including guidelines from the Reserve Bank of India require that credit and fraud related decision remains auditable and transparent. Therefore, beyond achieving high predictive accuracy, our XG Boost model must also provide a clear explanation for its prediction. To achieve this, we conducted a future importance analysis using an XG Boost gain-based importance metric. The results are shown in figure 6.1. The most influential feature of IP region mismatch contributed approximately 28% of the model predictive power. This indicates that discrepancy between an applicant's declared location and their actual network location are strong indicators of potential fraud.
The second most important feature is geolocation consistency at a 15.5%, followed by a device change rate at 10.1% and application frequency at 9%. Together, these findings shows that a model primarily relies on a behavioral and location-based signal rather than an obscure or difficult to explain variables. From an operational perspective, this provides several benefits. Fraud analysis can quickly identify the key risk factor behind the flagged application. Loan officer and risk manager gain greater confidence in an automated decision because the model reasoning is transparent. In addition, financial institutions can use this evidence to support regularity, compliance, and prioritize investigation on the highest risk cases, reducing operational costs. Finally, in line with our commitment on radical transparency, we acknowledge that the model is not perfect. It may underperform when fraudsters successfully mimic legitimate customer behavior, uses a sophisticated location masking technologies, or when a new fraud pattern emerges that were not represented in the training data. Recognizing this limitation is essential because effective risk management depends not only on understanding when a model works but also an understanding where it can fail. Thank you.
This final chapter summarizes the key conclusions of the study and presents a practical roadmap for implementing the proposed fraud detection model. This study confirms that XGBoost with threshold optimization delivers better fraud detection performance and stronger financial impact compared to logistic regression baseline. A key contribution of this research is proving that business-oriented threshold calibration plays a major role in reducing fraud losses and optimizing costs. To ensure successful implementation, a four-phase deployment strategy is proposed. Phase 1 focuses on offline validation using historical data. Phase 2 introduces pilot testing shadow mode without affecting live decisions. Phase 3 involves full system integration using API deployment, while Phase 4 focuses on continuous monitoring, retraining, and performance evaluation. Overall, the roadmap demonstrates that the proposed solution is technically effective, operationally feasible, and scalable for financial institutions. In conclusion, this study shows that combining machine learning with cost-sensitive decision optimization can transform fraud detection into a measurable business value driver. Thank you. That is all from me.